On time for the USS Hornet. I'd like to welcome everyone to the Science from and of the Moon parallel session this morning. Our first speaker is going to be giving his talk remotely. This is Steve Furlanetto, and he'll be talking about the insights into the first stars from low-frequency radio observations. And go ahead, Steve.
Thank you. Apologies for not being able to be at Ames, but thanks to the organizers for letting me dial in. So today I'm going to be talking about what we can learn about astrophysics from what we have learned, or sort of learned, from the ground, but hope to learn more about from the moon soon. So I'm going to be basically following up on Jack Burns' talk yesterday about cosmology from the moon. This is a sort of orientation slide showing the timeline of the universe with the Big Bang at the left to the present day at the right. And there are a bunch of important epochs shown here. Near the left is the recombination era. That's when the cosmic microwave background was last scattered. And the important point for this talk is that that means that after that point, the universe became neutral. It remained neutral for about 13.5 billion years, or 12.5 billion years, excuse me, until enough stars had formed and produced ionizing photons to render that gas, render the intergalactic gas ionized in an event we call reionization. And that happened about 1 billion years after the Big Bang, or about 12.5 billion years ago. That is just about also the limit of our current understanding of galaxies. So we can study galaxies in detail out to the present day. And as I'll show in a moment, we found them through the sort of end of this reionization era. But out of our vision so far is the formation of the very first stars and galaxies in the universe's history. And that's an event that we call the cosmic dawn. And it's extremely important for understanding the origins of complexity in our universe. So that's what we're trying to learn, and where we'll get to soon. But so far, what we know about these early generations of galaxies come from pretty traditional astronomy measurements. You look at a blank patch of sky and you try to find very faint, distant galaxies. So the Hubble telescope and soon JWST do this. And HST so far has helped us kind of measure the abundance of bright galaxies out to about 500 million years after the Big Bang. And for the purposes of this talk, the important result of that is simply that those galaxies behave very similarly to galaxies at the present day. Okay, so on a big picture level, we can understand them with the same kind of models that we use for normal galaxies later on. Unfortunately, even with JWST, we are not going to be able to push back to the era of the very first stars. So we want new probes to be able to do that, and one of those is the spin flip, or 21 centimeter transition of neutral hydrogen. So this comes from the electron spin changing directions, and because of the magnetic interaction with the proton spin, that produces a photon with a wavelength of 21 centimeters. However, this photon would have been produced in the early universe, and as the universe expands to the present day, it will have, its wavelength will have increased of order 10. And that means that we're going to observe these photons to have frequencies of 20 to 200 megahertz or so if we're studying this early cosmic dawn era. And as it turns out, that's a very difficult regime to observe from the ground, and that's the main reason we would like to go to the moon. I'll get back to that later. Okay, so now I want to kind of show you a history of the universe in this spin flip transition. So the left panel here is showing a snapshot of a simulation of what this transition would look like at various times. And the right panel is showing the average intensity of the signal as a function of time or observed frequency. So the left side of that right panel, low frequencies, corresponds to early in the universe's history, and the right side will be relatively late. So we're going from before the formation of the first stars here to this reionization era 1 billion years after the Big Bang. Okay, so before the first stars formed, the universe is a pretty boring place. And so I'm guessing on your screen, you just basically see a green. There are tiny little blue splotches there, which are just density fluctuations growing in the universe. And these are before the first stars. So the only thing that would change the signal here is some exotic physics, dark matter, black holes, stuff like that. As time goes on, this early signal fades away. And until the very first stars form. When those first stars form, they flood the universe with ultraviolet photons, and those photons turn on this 21 centimeter signal, and they turn it on in absorption. Okay, so in the snapshot, you're seeing little blue patches, and those are regions around these first stars that are being illuminated, and we're starting to see them show it in absorption against the cosmic microwave background. That will persist until the remnants of these first stars produce X-rays, okay? And those X-rays flood the universe and start to heat the gas and turn it from absorption into emission. So now the red splotches in the snapshot are regions near these first black holes that have been heated. The blue are regions that are still being heated, okay? But eventually the whole universe is heated, and we see this signal in emission against the cosmic microwave background now. And the last thing that happens is those first sources produce ionizing photons, which destroy the neutral hydrogen, right? And that means we don't see a 21 centimeter signal from the black patches at all. And as the whole universe gets ionized, the signal fades away, okay? So there's a rich astrophysics in the signal, and the really cool thing is that it's sensitive to the entire radiation background of all of the stars in the universe, even those in sources that are so faint we can't pick them out with our telescopes. So this is complementary to like JWST observations, which will look at bright things. This will allow us to see the very faint things, and it allows us to push to the earliest stars to have formed. Okay, right now is a very exciting time for this because about 1.5 years ago, Judd Bowman and the EDGES team announced the first detection of this 21 centimeter signal. Right, so this is their data. What they found was an absorption trough about 200 million years after the Big Bang, okay? And as I'll discuss, there's very confusing aspects to the signal, and it is very controversial. So what I want you to do is, I'm going to tell you how we interpret it, but at the very least, that's an example of what we can learn from similar lunar observations in the future that are hopefully less prone to contamination. All right, so now the right panel here is showing this 21 centimeter background again. The kind of gray band is a mock-up of that EDGES detection. And the black curve is showing what we would predict this signal to look like based on our models of the galaxies we can see. Okay, so the left panel is showing the galaxy abundances that we can measure along with fits to them, right? And as I said, simple models reproduce all the galaxies that we can see, more or less, at least the gross properties of them. So what we've done is take those simple models and just extrapolate them to earlier times. And what happens is you do not fit the EDGES signal, right? You get 3 things wrong. One thing you get wrong is the shape of the signal. The observation is too narrow, okay? I'm not going to talk about that again because that's sort of the least interesting of these problems. The next thing you get wrong is that the predicted signal is not deep enough to match EDGES. So remember, the prediction is the solid black line here, okay? I'll get back to that depth later. For now, the dashed line just says, well, we got the depth wrong, let's make it deeper. Even if you do that, though, you can see that it doesn't match up in frequency, which corresponds to time, right? So the prediction of the galaxies we can see does not start the signal off early enough. If we want to fix that, what we need to do is make more stars early in the history of the universe, okay? And there are 2 ways to kind of think of doing that. One is you simply say that at early times, galaxies produce stars more efficiently. Another slightly more sophisticated way is to say that, well, we've only seen the very bright things. So you could imagine making the star formation more efficient in small clumps of stars. We haven't seen those yet, so we can't rule that out either. And that works because at very early times, only small things are around to form stars, okay? So in this panel, I've done the second, which is make star formation more efficient in small halos, small clumps. But the problem is on the right, you can see that when you do that, you no longer match the observations of the abundance of bright galaxies either, right? You start to get into a regime where things are conflicting, okay? So the bottom line is what this edges detection tells us is that you need to make stars more efficiently in small or early things. And that's the first hint we've ever seen for star formation working in some exotic way, okay? And that's exciting in light of this cosmic dawn era because we expect the very first generations of stars to form in exotic ways, okay? Normal present-day stars form, they need to cool in order to get to the high densities to start fusion, okay? And the way they do that cooling is through heavy elements. But heavy elements weren't created by the Big Bang. And so the first generation of stars have to work differently. And it turns out they probably are more massive, okay? So now let's think about, can these exotic first generations of stars help us to understand edges? And the answer is yes, okay? So this is some work, ongoing work by my graduate student, Rick Mebane. And what he basically did is built a model of these exotic population 3 stars and predicted the 21 centimeter background from it to see if we could match the edges detection, right? So now these panels are showing the edges detection as the light gray, and the different curves you're seeing are different implementations of our model. Okay, so we've never seen these population 3 stars. We have little idea what they're really like, so one can make a variety of assumptions about them, and our model is built to allow for all of these different assumptions. But the important thing that happens is that in a wide variety of those assumptions, we more or less get the timing right for this signal. Okay, so it's not unreasonable to think that population 3 stars can fix one of our problems, right, and push the signal to happen earlier, to turn on earlier. Now there's that second problem, which is that we didn't get a deep enough signal. Okay, can we fix that? Right, well, that's harder. So it turns out that the depth of the signal, in order to get it large enough, you need to do one of 2 things. The first thing you could do is make the gas colder than you expect from an expanding universe. That requires exotic interactions with dark matter, basically, okay? If that's the case, then those exotic interactions should be happening before the first stars form as well, and so you would see changes in the very, very low frequency side, and you can study that with Dapper or other lunar arrays. The second thing you can do is say that, well, the gas is the temperature we thought it was, but it's absorbing against a brighter background. That could be a bright background generated by exotic physics, or it could be, maybe it would be great if it could also be generated by the same population 3 stars that are fixing the timing, okay? So we also used Rick's models to look at that. It turns out that, as you can see in the cyan curve in the top, you can write down models that reproduce the depth as well. However, it's not easy. Okay, you basically need to fine-tune things in ways that we can't explain. So in particular, you need to make these first stars 50 times more efficient at producing radio waves than they are at anything else, and than local comparable sources are. Okay, so it can be done, but it seems unlikely. All right, so that's kind of where we stand in understanding the 21 centimeter signal right now. Again, we're not sure that this hasn't been confirmed yet. Okay, so this is all very preliminary inference. But the moon is great because it's going to allow us to follow this up, both at lower frequencies, and that will allow us to look before the first stars form and separate kind of this exotic physics from astrophysics. And second, to study the cosmic dawn era with much cleaner systematics. The moon is a much nicer, has much less interference, has no ionosphere, and so it's easier to interpret the observations there. So with things like Dapper that will study this global signal, we can do it better than we've been able to do it from the ground. And in the future, with Farside and the lunar arrays that it might grow into, we can start to actually study different aspects of the signal, like those maps that I showed, instead of just the average intensity, which will teach us a lot more about astrophysics as well. All right, so I will stop there. I think I'm probably out of time. But thank you again for letting me call in remotely.
Okay, thanks, Steve. Does anyone have a quick question for Steve? We have the speaker that we can share around. No questions? Okay.
Hello, Alex Hedges from University of Michigan. You say that one of the fine tunings that your model does to match the results is to have 50 times more efficiency in creating radio waves for the first stars. Does that imply a breakdown of like the black body emission spectrum, and how would you reconcile that?
So these are the radio waves would come not from the stars themselves, but from their remnants, the black holes. So these are probably very massive stars, and so under certain mass ranges, they leave relatively massive black holes, and then those black holes can accrete gas. During that accretion process, in local sources at least, you get lots of fast electrons, and those electrons produce synchrotron emission and inverse Compton. Okay, so you get a non-thermal spectrum to begin with. The problem really is that the synchrotron emission has to be much more efficient to produce these enough radio waves. However, the same sort of non-thermal electrons magnetic field system would also be producing higher energy photons, X-rays. And if you crank up the radio waves by a factor of 50, you might expect also to crank up the X-rays by a factor of 50. But if you do that, the lower panel here shows that you also kill the signal, right? So you need to increase the non-thermal processes that make radio waves without increasing other non-thermal processes, which is why I think it's hard. It's going to be hard to arrange. I'm sure it can be done, but it's a fine-tuning kind of thing.
Weird. Thank you.